In this video, we'll discuss infinite series of real numbers and what it means for an infinite series to converge to a value. Let a sub n be a sequence of real numbers. An infinite series, denoted with this capital sigma, indexed from n equals 1 to infinity of a sub n, is the sum a1 plus a2 plus a3 plus a4, etc. We define the corresponding sequence of partial sums, Sm, by letting the mth term be the sum of the first m terms of our sequence an. So we would write that Sm equals a1 plus a2 plus a3 plus ... plus am. We say that the series, sum n equals 1 to infinity of an, converges to S if the sequence Sm converges to S. Let's consider a few different examples of infinite series and write out the sequences of partial sums. Consider the series 1 plus 1 plus 1 plus 1, etc. The partial sums are 1, 2, 3, 4, etc. And so their sequence increases forever, diverging. And so we'll say that the series diverges. Consider the series 1 minus 1 plus 1 minus 1. The partial sums of this series are 1, 0, 1, 0. And that's not tending toward either infinity, but that's also a divergent sequence. So this is also a divergent series. Now consider the example of the sum from n equals 1 to infinity of 1 over n squared. So this is the series 1 plus a fourth plus a ninth, etc. The mth partial sum of this series, Sm, is the sum of the first m terms, so 1 plus a fourth plus a ninth plus up until 1 over m squared. If we want to argue that the series converges, we need to argue that this sequence of partial sums, Sm, converges. Since each term of the series is positive, this is an increasing sequence of partial sums. So if we can show that it's bounded above, we'll be able to apply the monotone convergence theorem and conclude that it's convergent. Since we're looking for an upper bound, I want to write down something that's greater than this, that's simpler to work with. So in every term after the first, I'm going to replace one of the factors in each denominator with the integer 1 less than it, writing that this whole partial sum is less than 1 plus 1 over 2 times 1 plus 1 over 3 times 2 plus 1 over 4 times 3 plus ... plus 1 over m times m minus 1. And then I'm going to replace each fraction with a certain difference. So the first one will be replaced with 1 minus a half, the second one with 1 half minus 1/3, the third one with 1/3 minus 1/4, and that last term with 1 over m minus 1 minus 1 over m. And this is an equality. You can check by subtracting the fractions that this works, or you could arrive at this using partial fraction decomposition on 1 over m times m minus 1. But just in the small cases, you can verify that 1/3 minus 1/4 is in fact 1/12 by obtaining a common denominator. And writing the series like this allows us to make a bunch of cancellations. This is called a telescoping sum, and all we're left with is 1 plus 1 minus 1 over m. Since m is positive, that's less than 2. Since our sequence of partial sums is increasing and bounded, it's convergent by the monotone convergent theorem, and thus the original series is a convergent series. Now we don't know what it converges to. We can't say that it equals 2. It's going to be something less than that, but it's difficult to say exactly what the limit will be. Let's consider another example, the series n equals 1 to infinity, 1 over n. This is called the harmonic series, and its terms are 1 plus a half plus a third plus a fourth plus a fifth, on and on and on forever. And this is a classic counterexample to a Calc 2 student's basic intuition that if the terms of a series tend toward 0, it must be convergent. The converse of that false intuition will be true, that if a series is convergent, its terms will have to tend toward 0, and that'll give us a way to test for divergence. But this series turns out to actually be divergent, even though the terms get smaller and smaller and tend toward 0. The mth partial sum, Sm, would be 1 plus a half plus a third up until 1 over m. And in order to demonstrate the divergence of this series, we'll show that its sequence of partial sums is unbounded. We've already proven that any convergent sequence must be bounded. So if we can demonstrate that it's unbounded, that'll show that the series diverges. Let's observe that if we write out the fourth partial sum, 1 plus a half plus a third plus a fourth, we can say that it's greater than 1 plus a half plus a fourth, which equals 2. And if we write out the eighth partial sum, 1 plus a half plus a third plus a fourth plus a fifth plus a sixth plus a seventh plus an eighth, we can group terms like this and write that this is strictly greater than 1 plus a half plus a fourth plus an eighth plus an eighth plus an eighth plus an eighth, which equals 2.5. And we're going to be able to proceed similarly, going to the 16th partial sum and using the next 8 terms to get an extra 1/2 to demonstrate that 3 can't be an upper bound. And we'll be able to continue to extend this argument to show that there can't be any upper bound. For each additional increase of 1/2, we needed twice as many terms as the prior increase, which is why we considered S4, then S8, then S16, doubling the number of terms each time to bump that upper bound up by 1/2. So in general, let's consider S sub 2 to the k for some natural number k. Let's write out the partial sum S sub 2 to the k, 1 plus a half, plus a third plus a fourth, plus a fifth up through an eighth, plus ... all the way up through our last cluster, which will be the second half of the terms, written as 1 over 2 to the k minus 1 plus 1 plus ... plus 1 over 2 to the k. And then we apply the same inequality to decrease each term to the lowest term within its set of parentheses, writing that the whole sum is greater than 1 plus a half plus a fourth plus an eighth plus an eighth plus an eighth plus an eighth plus, and then our last set of parentheses will be a 1 over 2 to the k plus ... 1 over 2 to the k. So we've made each of those terms smaller as well, and by construction there will be exactly 2 to the k minus 1 of those terms, and so that whole sum will also be 1/2. So we can write each set of parentheses as the number of terms there were times its value. 2 times a fourth, 4 times an eighth, 2 to the k minus 1 times 1 over 2 to the k, and each of those is 1/2, which means this total sum is 1 plus k times 1/2. And as k grows, this is unbounded. This continues to increase forever, and our partial sums are greater than this. So we know that our sequence of partial sums is unbounded and thus divergent, and thus the harmonic series is divergent. Now each of those two arguments that we just made for the convergence or divergence of a certain series felt quite creative and out of the blue, with algebraic manipulations that may have felt unmotivated. One of our main goals with the study of series is to establish machinery for demonstrating convergence or divergence. We'll learn a series of tests that we can apply to series to conclude whether they converge or diverge. And in real analysis, but in mathematics more generally, the difference between a trick and a technique is really mostly about the number of times that you've seen it applied. When you first add and subtract the same thing, setting up the triangle inequality, it feels like it comes out of nowhere. But then you start to see it as more of a pattern. The same thing will be true with a lot of these algebraic manipulations of series. The technique we just applied to the harmonic series can be generalized and applied to all sorts of series in a test called the Cauchy Condensation Test. Suppose a sequence a sub n is decreasing and satisfies a sub n is greater than or equal to 0 for all n in the naturals. That is to say, all the terms of this sequence are non-negative. Then the series, the sum n equals 1 to infinity of a sub n, converges if and only if a certain related series converges. That series is the sum from n equals 0 to infinity of 2 to the n, a sub 2 to the n, whose terms can be written out as a sub 1 plus 2a2 plus 4a4 plus 8a8, etc. This is a stronger statement than the specific case we used with the harmonic series, because that only went one direction. We made the terms smaller and argued that since the smaller series was unbounded, so was the bigger one. And we'll do that here as well, but we also get the reverse direction. This is an if and only if. Now if you just started with the series a1 plus a2 plus a3 plus a4, etc., and you knew that the terms were decreasing, and you wanted to write down another series that was simpler to make arguments about and that was smaller, you might think to compare it to something like a1 plus a2 plus a4 plus a4 plus a8 plus a8 plus a8 plus a8. And this is kind of what we did with the harmonic series, and you would notice that you only have one a2 term and two a4 terms, half as many as the index. And so you might wonder why the theorem has the index matching the coefficient. If you set up the theorem a little bit differently, to have the coefficient as half the index for all the terms after the first, it would still hold. This is because, as we'll prove next video, if a series converges, then double that series, or any scalar multiple of that series also converges. So the extra factor of 2 doesn't end up mattering. So we just want to state the theorem in the most elegant way, and having the coefficient match the index is quite nice. Since this is an if and only if proof, we'll need to have two directions. Let's start by assuming that the series of the an terms converges. By the same logic we used with the harmonic series, the 2 to the kth partial sum, s sub 2 to the k, the sum of the first 2 to the k, a sub n's, is greater than or equal to the sum that results from increasing each index to the nearest power of 2. Because since the terms are decreasing, increasing the index decreases the value of the partial sum. We can group the terms on that right-hand side as a1 plus a2 plus 2a4 plus 4a8, etc., and we can write that that's equal to a1 plus 1/2 of the series n equals 1 to k, 2 to the n, a sub 2 to the n. Since the series a sub n is convergent, the sequence Sn of partial sums is bounded by some real number m. And so that expression, a1 plus 1/2 the sum n equals 1 to k of 2 to the n, a sub 2 to the n, is less than or equal to m. And doing a little bit of algebra, this will be a bound on the 2 to the kth partial sum of the series that we're trying to show converges. We could say subtract 1/2 a1 from both sides, and then what we'll have left on the left-hand side is exactly half the series we're interested in, so we can multiply by 2 and write that the sum from n equals 0 to k of 2 to the n, a sub 2 to the n, is less than or equal to 2m minus a1. And since the sequence of partial sums of the series n equals 0 to infinity 2 to the n, a sub 2 to the n, is increasing, then this is also going to be a bound for all of its partial sums, not just those that are powers of 2. And so by the monotone convergence theorem, the sequence of partial sums converges, and so the series converges. For the other direction, we could either assume that the original series a sub n is divergent and show that that forces the new series of n equals 0 to infinity of 2 to the n, a sub 2 to the n to be divergent, or we could start by assuming that the series n equals 0 to infinity of 2 to the n, a sub 2 to the n is convergent, and use that to show that the series an is convergent. Let's use that second strategy. So assume that the series n equals 0 to infinity, 2 to the n, a sub 2 to the n, is convergent. Now we'll try to bound the partial sums of the series an to argue that it must be convergent. And we could look at the 2 to the kth partial sum and compare things directly, but we actually don't need to because of the direction the inequalities will flow. Let's just consider the kth partial sum, a1 plus a2 plus ... up through ak. And we can say that this is less than or equal to what we would get if we added a bunch more terms on, effectively going up to the 2 to the k plus 1 minus 1 partial sum, and we'll see in a moment why that's a convenient choice. We'll group terms together, but this time group terms in the opposite direction, because we'll want to actually decrease the indices to increase the overall value. So instead we'll group a2 with a3, and a4 with a5, a6, and a7, etc. And in that last grouping, we'll have a sub 2 to the k up through a sub 2 to the k plus 1 minus 1. And then in each of these parentheses, we'll decrease the index, a3 down to a2, a5, a6, a7, all down to a4, so that the total sum is greater. So this new sum is greater than or equal to the prior sum. And counting the number of terms in each parenthesis, this is equal to a1 plus 2a2 plus 4a4 plus ... plus 2 to the k a sub 2 to the k, which is exactly the kth partial sum of the series we assumed to be convergent. Since we assumed that series to be convergent, there exists a bound, big M, in the reals that's greater than or equal to all of its partial sums, and now we know that that same big M is also a bound for all of the partial sums of the series a sub n, whose partial sums we know to be increasing, by the non-negativity of the terms an, and so by the monotone convergence theorem, that sequence of partial sums converges, and thus the series an converges as well. So we've shown both directions of the Cauchy Condensation Test. One of the first main applications of this Cauchy Condensation Test is to prove that the series n equals 1 to infinity of 1 over n to the p converges if and only if p is greater than 1. So the harmonic series we looked at was the p equals 1 case, and that ends up being right on the boundary. That's the largest value of p that still diverges. We also looked at that p equals 2 case, and we demonstrated that it converges. We'll be able to prove this corollary once we establish a few more basic facts about geometric series, which we'll do in the next video.